Okay, in this video, I am going to go through the Edexcel A-level Chemistry paper from June 2019. This is paper 1, Inorganic and Physical Chemistry. I will probably just do half of the paper in this video and the second half in the later one. Okay, so the first question is pretty straightforward. Number 1. Talking about an O18 atom, how many of the protons, neutrons, electrons have we got there? Well, if you look in your periodic table, oxygen is atomic number 8. So in that particular isotope, we've got 8 protons, 10 minus 8 neutrons. That makes 10. So 18 minus 8 neutrons is 10. And then number of electrons, it's an atom. So the number of electrons are equal to the number of protons. So it's going to be 10 electrons, sorry, 8 electrons. So the answer there is A, this one. 8 protons, 10 neutrons, 8 electrons. Kind of pretty easy question, not much more than GCSE really. Okay. Now we've got the mass spectrum of bromine molecules. It tells you you've got roughly equal proportions of the 2 isotopes, the 79 bromine and the 81 isotope. So what's the mass spectrum going to look like? Well, when you put bromine exists as diatomic molecules, of course. And when you put it in the mass spec, some of those diatomic molecules will break up into atoms. So you are going to see peaks at MZ 79, it's bromine atom. You're also going to see one at 81. Right, but in addition to that, you're going to see things due to the diatomic bromine molecule. So if you get so Br2, of course, you can have 2 79s together. 2 of the 79 isotopes. That's going to give you an MZ of 158. You could have a 79 and an 80 together. That's going to give you an MZ of 160, and you're going to get an 80, 2 lots of 80. That's going to give you 162. Right, so this one is obviously wrong because there's no diatomic molecules in there, but the others are all possible. They're all possible because this bit here, you've got roughly equal amounts of 79 and 81, so that doesn't let us narrow it down at all. So we've got to think about what first of all, we can also eliminate this one because this one has only got a 158 and a 162, and there should be a 160 peak there as well. So the question is it C or is it D? Well, D is going to be the right answer because if you think about this one here, 79 and 80, there's 2 ways of having that. That's doubly, that is got double the possibility of having it. So this middle peak at 160 should be twice as high as the other 2. So D is the correct answer there. Okay, if you wanted to look at it in terms of probability, you could say, right, we'll do one of those little probability trees. You could say, right, here's the molecule. So we'll say, right, let's say the first one is 79. Right, so you look at the Br2 molecule. If the first is a 79, that's a 1 in 2 chance of that. Or the first one is 81, that's also a 1 in 2 chance. Now you look at the second one. Well, the second one could be a 79. That's also a 1 in 2 chance. Or it could be an 81. That's also a 1 in 2 chance. So, and the same here. 79 or 81, 1 in 2 chance. So you can see the chance of each of these outcomes is a half times a half. So that's a quarter, and a quarter there, and a quarter there. Right, what's going to be the MZ of those 2? Well, 79 and 79, that is going to be 158. So there's a quarter chance of a 158 peak. If you do this one, 79 followed by the 81, the MZ is 160. And of course, it's this 160. You do 81 first, and then 70 back to 160. And then this one is going to be 81, and the 81 is going to be 158. So you can see that these two, a quarter plus a quarter, makes a half. So that is twice as likely as that one or that one. So the correct answer is D. Okay, the total number of electrons in all p orbitals in the chloride ion. Well, we've got chlorine here. So a chloride ion is going to have the 2p shell completely filled up, 2p6, and also the 3p shell is going to be completely filled up. Chlorine, the atom, has got 3p5, but this is an ion, so it's 3p6. So the total number of p electrons is 6 plus 6. We've got 12. So the answer there is C. Okay, which of these isoelectronic ions has the largest ionic radius? Isoelectronic mean they've got the same electronic structure. So if you look at any of those, for example, if you look at O2 minus, well, oxygen is 1s2, 2s2, 2p4. So it's 2 minus is going to be 2 extra electrons in the p shell, 2p6. So they've all got that electronic structure. So they've got the same number of shells filled. Which one is going to be the largest? Well, the largest one is going to be the one with the smallest nuclear charge, because the nuclear charge holds the electrons in closer. So aluminium is going to be the biggest because that's the most number of protons. Aluminium has got 13 protons. And of course, nitrogen, this is going to be the largest one because that's got the smallest number of protons. It's only got 7 of them. Okay, question 2. About chlorine, bromine, and iodine. Okay. So here, an excess of potassium bromide, and this excess is important for the later part of the question, was added to chlorine water and the solution turned orange. Write an equation for the reaction. Okay, so we've got KBr and chlorine, don't need state symbols. Right, chlorine it's got a greater affinity for the electrons, if you like. It's a better oxidizing agent than bromine, so that's going to remove the electrons from the bromide ions. Again, you're going to end up with chloride ions, so you're going to end up with KCl. And when you remove the electrons to bromine, of course, they're going to form diatomic bromine, and I just need to do that to balance it. Okay, so that's the equation. Right, now the next part of this, it says silver nitrate was added to the mixture in excess. Okay, and dilute ammonia was then added. Only some of the precipitate dissolves. Okay, let's see what's happening here then. So the mixture in A, we've got an excess of potassium bromide. Okay, so at the end, we're going to have some bromide ions left over because there's an excess of it. We're also going to have some chloride ions left over. Well, not left over, that have been made. Now, when you add the silver nitrate solution, you're adding the Ag plus ion, and of course, silver chloride is insoluble. So you're going to get a white precipitate of that. And you're also going to get a bit of silver bromide precipitate because of this important bit here, there's excess stuff there. And that's a cream precipitate. Now, when you add dilute ammonia, which of those precipitates will dissolve? Well, Ag, that does dissolve in dilute ammonia. So the silver chloride precipitate will dissolve, but silver bromide will not dissolve in dilute ammonia. Okay, so that is why not all of it dissolves. Okay, so it's quite important that you realize that excess, an excess of potassium bromide. Okay, aqueous potassium bromide was added to iodine instead of chlorine water. There's no reaction. Okay, so what we've got there, we've got I2 and Br minus ions. No reaction there because what doesn't happen is you do not get iodine taking the electron off the bromine. Sorry, that doesn't happen. And there's one mark. Okay, now it's not going to be good enough to just give a GCSE explanation there and say bromine is more reactive than iodine. You've got to talk about in terms of electron transfer. So what I would say is I would say that I2, well, it doesn't want the electrons as much as the Br2 does, but I2 is a weaker oxidizing agent. That's what I would say. Br2. You could say the converse of that. You could say that if you like, that the iodide ion, that is a stronger reducing agent than the bromide ion, because iodine is more willing to lose the electron in the bromine. Okay, so you could say it that way around. Okay, chlorine undergoes disproportionation when it reacts with hot aqueous sodium chloride. Complete equations for this, right? And then next bit, you've got to explain in terms of disproportionation, why it's a disproportionation. So what I would do is the oxidation numbers will actually help you balance this equation rather than do it by trial and error, right? The oxidation number of chlorine there is 0 in Cl2. Here it's -1, and here it is +5 in the chlorate ion here. So if we think about each chlorine atom there, that one going to there, well, the oxidation goes at 5, so that's going to be 5 electrons lost. So that means this one here, like that is only gaining 1 electron. And so that means that arrow there, that must happen 5 times for every time the green one here happens. Okay. So what I'm going to do there is I can put in colors. We're getting a bit messy here, but I can put a 5. So we need this one to happen 5 times. So we do 5 chloride ions for every 1 chlorate. So there's a 1 in front of the chlorate. That means we need to put a 3 there because we need 6 chlorine atoms altogether. Now we just need to think about the balancing for the waters. All right, let's think. If we put a 4 there, that's not going to work. So let's try 6. Yeah, let's try put a 6 there. So we've got 3 H2Os. Okay, that will be right now because we've got 3 oxygens in there in the H2O, and we've got 3 oxygens in the chlorate ion. So that makes a total of 6 oxygens, and we've got 6 on that side. So you can use the oxidation numbers to help you balance there, and then just do the water and the hydroxide bit sort of by trial and error. Explain why this is disproportionation reaction, then this next bit of the question. Why is it disproportionation? Well, it's disproportionation because the chlorine becomes oxidized. One of the chlorines in Cl2 gets oxidized because the oxidation number rises to +5 in the chlorate, and the other one is reduced because its oxidation number goes down to -1, and that's in the chloride ion. Okay. Okay, number 3 then. Okay, so we're on to enthalpy change of neutralization, right? And it stays here. The enthalpy change of neutralization is when an acid and an alkali react to form, that's quite important, to form 1 mole of water. Okay, right. So that's delta H for neutralization. Now, if you look at this equation, how many moles of water are we forming here? We're forming 1 mole in that water. Okay, so the enthalpy of neutralization is delta H for that reaction as it is stated in that equation there. Okay, that'll be important we come to that. Okay, so it says, first of all, 50 centimeters cubed of sodium hydroxide was placed in the polystyrene cup. The initial temperature was measured. Now, which piece of equipment has the smallest measurement uncertainty for the measurement of the sodium 50 centimeters of sodium hydroxide? Well, we can forget about that one, B, first of all, the measuring cylinder, because it's got a really big uncertainty there of 1 centimeter cubed. Now, the burette, you might be tricked into thinking, right, look, that's the smallest one. But when you use a burette, of course, you take two readings, the initial reading and the final reading. So that means you've got to multiply that uncertainty by 2. So the total uncertainty there is going to be 0.1 plus or minus 0.1 centimeter cubed. For measuring 50 centimeter cube pipette, right, that's going to be smaller, that one there. Look, that's only 0.08. So that's better than the burette. And you may be tricked into thinking, oh, this one's even better still, but it's not, because look, it's a 25 centimeter cube pipette. So you'd have to multiply that by 2, because you need to do 2 lots of 25, and each time you'd have an error of 0.6. So the total error there would be plus or minus 0.12, wouldn't it? Yeah, which is bigger than that one. Okay, so that's not going to be, so the correct one there is to use the 50 centimeter cubed pipette. Okay, now we've got to do the calculation bit here. Okay, to calculate the delta H for this reaction. So they're adding, so the previous part of the question, it said they had 50 centimeters cubed of NaOH of concentration, 1 mole per decimeter cubed in the polystyrene cup. Then they're going to add the propanoic acid to it. Okay, so we've got to work out delta H. So the two equations we're going to use, Q, the quantity of heat released in the beaker, is mc delta T. And then we need to, that's the quantity of heat released in the experiment. We need to convert that to delta H. So delta H is equal to Q over the number of moles. Now it said here, the enthalpy of neutralization is when you form 1 mole of water. 1 mole of water. Okay. Now to form 1 mole of water, you use up 1 mole of the propanoic acid and 1 mole of NaOH. So we can, so this equation here is going to be delta H divided by the number of moles of the propanoic acid or the sodium hydroxide. And we need to check that neither one of those is in excess, okay? And we can see that they're not in it. So if you just look here, let's do the moles of sodium hydroxide. 50, 1 mole, so moles NaOH. Concentration times volume, 1 times 50 over 1,000, 50 centimeters cubed. 0.05 is the answer there. And that's the same number of moles of propanoic acid, because look, it's 50 centimeters of propanoic and same concentration. So here, delta H, we need to do Q over the number of moles of NaOH or propanoic acid, which of course is 0.05. Right, let's work out Q first of all. Right, M is the mass of the water there. Well, it tells us the density of the solution is 1 gram per centimeter cubed. Well, we've got 50 centimeters cubed of propanoic, 50 centimeters cubed of NaOH. So the total volume is 100. So that's going to be 100 for the mass, 100 grams. This heat capacity of water, specific heat capacity is 4.18. And the temperature rise, it tells us, is 6.5. Put those numbers into the calculator, we get 2,717 joules is Q. Now we need to convert that value of Q into delta H using that equation there. So delta H is equal to Q, 2717 over the moles of NaOH, that's 0.05. Work that out, we get a value there of 5,434,340 joules per mole. And importantly, we have to remember that it's going to be a minus sign there because it's an exothermic. The temperature's gone up, and you lose a mark if you forget that. It does ask us to give it in kilojoules per mole and to the nearest whole number. So the answer we should give is divide by that number by 1,000, 54, not 54.34, because it's the nearest whole number, kilojoules per mole. Okay, that was reasonably straightforward delta H calculation then. Okay. Okay, now it says here, all right, so instead of just measuring the maximum temperature, they've done this thing where you say you monitor the temperature throughout the reaction before and afterwards. Another experiment is carried out solution of ethanoic acid and sodium hydroxide, which graph shows the correct way the maximum temperature rise should be determined. Okay, right, now let's look at those 4 graphs. Right, so you can see that this one is wrong. Look, they're taking the temperature rise. The temperature you know, they've extrapolated this line back way past to when you added the NaOH. You added the NaOH there, so this is, they've extrapolated it back to here instead of here, so that's wrong. This one is correct. They've extrapolated the line back to where the point where they've added the NaOH there, and then they've extrapolated this line forward to get the temperature when they before you've added it. Okay, this one is wrong. That line should be extrapolated backwards, and this one is also wrong. That line should be, you know, going up there. Shouldn't be how they've done it. So the correct one is going to be B. Okay, explain what the data book for the enthalpy change of neutralization. Remember, enthalpy change of neutralization is when we're forming 1 mole of water. And what we're forming that from, we're forming it from OH minus ions and H plus ions. So how come is it different for ethanoic acid than it is? Why is it less exothermic? Well, ethanoic acid, of course, is a weak acid. I'll give you 1 mark for that. And why should we get less energy out? Well, it's because some energy is required to ionize the ethanoic acid. So most of the ethanoic acid is not going to be ionized. It will be like that, won't it? It's a weak acid. And the process of losing a proton and becoming that ion is endothermic. You need a bit of energy to do that. So that's why you get less energy out for the weak acid than for the strong acid. Okay, question 4, thermal decomposition of a metal nitrate. Now, it doesn't tell us what kind of nitrate it is, what kind of metal it is. And of course, group 1 nitrate, so like sodium nitrate, behave differently to group 2 nitrates and transition metal nitrates, which have generally, so we're going to have that formula. Okay, just to remind you, when you decompose these, you end up getting oxygen and nitrogen dioxide gas. You decompose them to the oxide, but with the group 1 ones, you don't get that. You just get oxygen, and it just goes to the NO3 decomposes to the NO2 ion. Okay, anyway, let's answer the questions. A glowing splint is used to test for one of the gases given off in the experiment. Okay, that of course is not a test for NO2, is it? It's a test for oxygen. So it's O2, and what will it do? It will relight the glowing splint. Right, and it says here, give the name and appearance of the other gas given off in the experiment when a group 2 nitrate is heated. Well, it's nitrogen dioxide, and it's NO2. And what does that look like? Well, it's a brown gas. And just to remind you, saying we have calcium nitrate, doesn't ask you to write this equation, but just to remind you, you're going to get the oxide, NO2, and some oxygen as well. Okay, equation for the decomposition of group 1 compound, sodium nitrate. What would happen there? Right, so You don't get NO2 given off there. You just get decomposition to the nitrite ion, which is NO2 minus, sorry. So you get NaNO2 and oxygen. Okay, describe the apparatus that could be used to compare the decomposition of metal carbonates and include how the rate of decomposition would be compared. Right, now metal carbonates decompose to give off carbon dioxide gas. Okay, it's only a 2-mark question, so they don't want anything too sophisticated here. So you're just going to decompose the carbonate and then test the gas to see if it's carbon dioxide. What's the test for carbon dioxide? Term lime water cloudy. And you could time how long it takes for the lime water to go cloudy. The quicker it goes cloudy, the faster the rate of CO2 production. So that means that the thing is decomposing more quickly. So time how long for the lime water to go cloudy. How would you do that? Describe the apparatus. So probably the best way of describing the apparatus is to draw it. So I would draw one tube here with a delivery tube coming out of it. So there's your carbonate, goes in there, and you're going to heat there. You're going to have a delivery tube coming out, and that is going to go into another tube containing lime water. So put some lime water in there and time how long it takes for the lime water to go cloudy. But when they draw diagrams like that, you must, you've got to draw it properly with the delivery tube going through the bung, and you've got to make sure the bung is there. They won't accept things like the bung like that and the tube coming out. They'd say that that's not going to work because, of course, the delivery tube is not going through the bung. So you don't have to draw a magnificent artistic diagram, but it does have to be accurate in that respect. Okay. B, explain why magnesium carbonate decomposes much more readily when heated than barium carbonate. Right, so I've drawn here is the group 2. At the top of the group, magnesium, calcium, strontium, barium. Right, of course, all of those carbonates have the following formulae: MgCO3, CaCO3, and so on. And the magnesium ion is 2+, and they're all 2+ ions, of course. And the carbonate ion is like that. Right, so the reason why is because as you go, these are all 2+ ions. What happens to the size of those ions as you go from magnesium to barium? They get bigger, but they're still only +2. So I would say the charge density decreases down the group. That means magnesium is the best at polarizing the carbonate ion. In other words, pulling negative charge across from the carbonate ion towards the magnesium. And that means when the ion gets polarized, the carbon-oxygen bonds are weakened. So that means you need less energy to break them. So they're easier to break, and so the compound decomposes more easily. Okay, so those 3 points, there's 3 marking points there. Charge density decreases down the group, so they're not as good at polarizing. So magnesium is the best at polarizing it. When you polarize the ion, you weaken the carbon-oxygen bonds. Okay, on to transition metals and catalysis. Okay, this one, reaction between iodide ions and peroxide of sulfate ions is catalyzed. Now, this is on the specification of this reaction. You should know this. You should know the equations for this. You should know this reaction sort of off by heart. to give a reason why the reaction between iodide and peroxide of sulfate ions has a high activation energy. Again, this is on the specification, but if you look, they're both negatively charged. The iodide ions and the peroxide of sulfate ions are negatively charged, and so they're going to repel each other. The activation energy is going to be high. Right. 2, explain with the aid of 2 equations how the iron 2 ions catalyze this reaction. Okay, so what I would do is I would break down this equation into 2 half equations first of all, and this is kind of your working out. You wouldn't show all the working out, you give the final answer, but I'll show. So you've got 2I minus, and that goes to I2. So we can see the iodide ions are getting oxidized there, and we need to balance that half equation. So we've got no oxygens or hydrogens to worry about. We've just got to balance for the negative for the charges. We've got 2 minuses on the left-hand side here, and so that means we need to put 2 electrons there to balance it. Let's do it for the peroxide of sulfate ion. Right, so that's like that, and that's going to decompose. That's going to decompose. Sorry, it's going to give us 2 sulfate ions. No oxygens to worry about there. We've got 8 on both sides. No hydrogens to worry about. We just got to balance with charges. Well, we've got -2 on the left, but -4 on the right. So we need to put 2 electrons on here. Okay, so we can see in the redox, it's a redox reaction. This one here, the iodide ions are losing electrons to electrons. Now, instead of giving, and in this one, the peroxide of sulfate are gaining 2 electrons. Instead of the iodine giving them directly to the peroxide of sulfate, it's going to give them 2 Fe3 plus ions. Okay, and if you give an Fe3 plus ion an electron, you'll turn it into an Fe2 plus ion. So we're going to need 2 of those, 2 Fe3 plus. And they're going to get turned into Fe2 plus ions. So we're going to cross that out. And the opposite happens here. So the peroxide of sulfate is taking electrons in, or who can give away electrons? Fe3 plus or Fe2 plus? Well, Fe2 plus can. So we've got 2 Fe2 pluses. And each of those, when you take an electron off it, is going to turn into an Fe3 plus. So that's the 2 separate equations that are occurring. Okay, those 2. And of course, if you add those together, all the ion species will cancel out, and you'll just end up with the original equation. So showing that the ion, the Fe2 plus or Fe3 plus ions are just catalysts. They don't get permanently changed in the reaction. Incidentally, it's sometimes a bit confusing to think, you get a bit muddled thinking, what should I put 2 Fe3 plus or 2 plus on which side? So a good check to make sure you've done it right is just check that your charge is balanced. So let's just check that. Look, on this side of the equation, we've got 2 minus and 6 plus there. So we've got +4 on that side altogether. On this side of the equation, yeah, we've got +4 there. So we have put them on the right side of the, you know, if you put Fe2 and where Fe3 should go, your charges wouldn't balance, and you'd realize you made a mistake and you could swap them about. Right. Okay. Now this carries on from this one. Sulfate 4 ions can be oxidized to sulfate 6 ions. So that's sulfate 4, oxidation number 4, sulfate 6, and it's catalyzed by cobalt ions. Okay. Now the cobalt 2 ions catalyze in a very similar way to the Fe3 plus. So they're going to do that. They're going to flick backwards and forwards between the +2 oxidation state and the +3 oxidation state there. Okay. That's how they're going to work as a catalyst. We've got to deduce 2 ionic equations to show how cobalt can catalyze a reaction in acidic solution. Okay, so right, what we've got to do is we've got to break down this equation into 2 half equations like we did with in the previous example. So I'm going to have SO3, the sulfate 4 ion, going to SO42 minus. Right, I need to then complete that half equation. So right, we've got 3 oxygens on the left and 4 on the right, so we need an H2O here. Balance for our hydrogens, well, we've got 2 hydrogens on the left, none on the right, so we need to put that there. Now I need to balance for charges, and you can see we've got 2 minus on the left, but on the right we've got 2 minus, we've got 0, so we need to add another 2 electrons there to make the charges balance. Okay, so you can see that the sulfur has become oxidized, it's lost 2 electrons. And what's the other thing is by water. So we've got a half O2, and water, right, has got an oxidation, oxygen has got an oxidation number of 0 there. The oxygen is going to get reduced. As remember, it always goes to water, H2O. So I need to balance for hydrogen. So I need to put 2H plus on that side of the equation. Now I need to balance for charges. Well, I've got 0 charge on the right, plus 2 on the left. So I need to put 2 electrons on the left. Okay. So you can see there, what's happening then is we have got, so this one is losing 2 electrons, this one's gaining 2 electrons. And just like we did before, right, so we need to put in cobalt ions, get rid of it, and okay. So we can see here, let's do this one first. Look, the oxygen is gaining 2 electrons. Who can give away electrons? A 2 plus or 3 plus? It's the 2 plus cobalt. So we want 2 cobalt 2 pluses there. And when each of those gives away an electron to the oxygen, we're going to end up with 2 CO3 plus on the right hand side. Okay, and let's do this equation now here. Right, so it's the opposite here. Look, we're giving away 2 electrons. So we're going to have each of those electrons are going to go to cobalt 3 plus ion. So we want 2 cobalt 3 plus there. Give them an electron, each one turns into a cobalt 2 plus. Okay, and just check your charges there. You can see that you have got, right, to make sure you've got your cobalt 3 plus and 2 plus on the right hand side. I'll just do the top one as an example. Well, what's the total charge on this side of the equation? We've got 2 minus on the sulfate, and we've got 6 plus, so that's plus 4 on the left. On this one, we have got 2 minus there and 2 plus, that's 0 so far. 2 times 2 plus, that's plus 4. So yeah, we have put the cobalt 2 plus and 3 plus on the right side of the equation. It's worth doing that check. Okay. So again, the cobalt and the iron are acting as oxidizing agents there by receiving electrons and giving away electrons, receiving electrons, giving away electrons. So they're flicking between the 2 oxidation states. A homogeneous catalyst. Okay, right. This is related also. Oxidation of ethane dioate ions starts slowly, then rapidly increases. Well, this you may remember is an auto-catalyzed reaction. And the catalyst. So that means that the catalyst is a product of the reaction. And the product of the reaction, which is doing the catalysis, is the manganese 2 plus ion. And again, an actual, I don't need to say that, but it's flicking between the Mn2 plus and the Mn3 plus oxidation states and catalyzing that reaction. So the correct answer is C. Okay, now this is about not homogeneous catalysts like in the previous case. This is about heterogeneous catalysts. Yeah. So that means you've got gases, the reactants in the gaseous phase usually, and the catalyst is in the solid phase. Okay, it says here, here's the strength of adsorption. Of course, in heterogeneous catalysts, yeah, the things have to adsorb to the surface of the catalyst, and that's where the reaction occurs. It says silver's not suitable for platinum because the adsorption is too weak. Give a possible reason why tungsten wouldn't be a suitable replacement. Well, it's the opposite here. Tungsten, it would probably adsorb it too strongly, which is not good because it means that the products wouldn't be able to be released from the surface of the catalyst easily enough, and it wouldn't be very efficient. Whereas platinum is kind of right there in the middle. doesn't absorb it too strongly or too weakly. And just be careful. You look at the mark scheme there. They're very clear that you've got to have that. If you write absorption, yeah, AB, that's wrong. You've got to use that adsorb. Okay, that word. Right. Here's a question about water. Okay, now water might be, so we've got water, H2O, and we've got hydrogen sulfide, which is H2S. Oxygen and sulfur are both in group 6 of the periodic table. We've got similar formulae for hydrides. Why might this be expected of a higher boiling point, but it doesn't? And we've got to talk about the intermolecular forces. Okay, that's 4 marks. So what they're probably looking for here is, why would you expect it to be higher? Well, because H2S has got more electrons. It's a bigger molecule. So that would mean the London forces, so in other words, the instantaneous dipole interactions, or the temporary dipole interactions, are going to be stronger. Okay. But it doesn't have a higher boiling point. Why not? It's because in water you have different kind of intermolecular force. You have H bonds, hydrogen bonding. Okay, so we've got 2 marks so far, and I think we need to say that H bonding is stronger. And then the final mark, I think it's probably you need to say, so you need more energy to break those. Okay. It says here that you don't have to talk about a description of the intermolecular forces of force. So you don't have to talk about what London forces are. You don't have to talk about how hydrogen bonds, you have a proton, which is delta positive, sorry, hydrogen atom, which is delta positive, being attracted to the lone pair. You're not going to get any marks for talking about that in this question. There's only 4 marks going. Right. Explain why both water and carbon dioxide have polar bonds, but only water is a polar molecule. Right, so we just look at that. Carbon dioxide, you've got no lone pairs, okay? You've got carbons forming two double bonds, so there's no lone pairs on the carbon. So the shape of that is going to be linear. It is symmetrical. That's pretty important. We've got symmetry there. Whereas if you look at water, oxygen does have 2 lone pairs, has 2 lone pairs, okay, and it's not symmetrical. Right, why have they polar bonds but only water is polar? Okay, why do they both have polar bonds? Is because oxygen is more electronegative than both carbon in the carbon dioxide, and it's also more electronegative than hydrogen in the water. So that means you are going to have polar bonds. We can show by that. Yeah, you can have polar bonds here as well. But why isn't carbon dioxide polar then? Well, it's because it's symmetrical. And so the excess charge on negative charge on this side of the molecule is exactly balanced by the excess negative charge on that side. So you've got an even distribution. Okay. Whereas with water, and you only got, I think we need to say here, water has got 2 lone pairs. The oxygen has 2 lone pairs. And so it is not symmetrical. And so you don't get that happening there. That will be enough for your 4 marks, I think. Right, pure water ionizes to form H3O plus and OH minus ions, although only to a very small extent. Draw dot cross diagrams of each of these ions. Well, you don't have to draw this, of course, because it's not asking you to draw the water, but I'm going to draw a dot cross diagram for the water molecule. Draw a bit bigger than that, just to explain. Right, so the dot cross diagram for that oxygen, we have a single covalent bond, so a dot and a cross in each one there, dot from the oxygen, cross from the hydrogen. The oxygen is in group 6, so it's got 6 dots, 6 electrons in that shell. I've only drawn 2, so we need 2 lone pairs, 1 there, 1 there. Now, when it forms the OH minus ion, what happens is you lose one of those H's. Let's say, see that one is going to go there. We're going to lose that. So the dot cross diagram for the OH minus ion is going to be like this. 2 lone pairs and a third lone pair. And that electron has come from the hydrogen. Okay, put a minus on there. And how does the H3O ion form? Well, this hydrogen I've drawn there has been, that leaves without its electron and forms a dated bond by one of those lone pairs there. So if I draw the H3O minus, so we're going to have okay, so we want a dot and a cross there, dot and a cross there, we want a lone pair there. And this hydrogen, we like to do that in red, so that's come along without any of its own electrons. And so that has a plus charge. Use dots for the hydrogen and crosses for the oxygen. I've just done it the other way around. You didn't read the question, so don't be like me and do it properly. Okay, sorry about that. I only just realized that now. Okay, an equation for the ionization of water. They give us there. Okay, the expression for the ionic product is that. They give the value Kw, so calculate the pH of water. How are we going to do that? Well, we know in pure water, in neutral water, we know that H plus ion concentration is equal to the OH minus concentration. So let's substitute that in there. So that gives us Kw is equal to H plus concentration squared. Okay. We want to find out the pH, so we need to find out the hydrogen ion concentration. So H plus is equal to the square root of Kw. So H plus concentration is the square root of 310 Kelvin. It is not the usual value we have at 298, slightly different. 2.4 times 10 to the minus 14. And take square root of that, you get 1.549 times 10 to the minus 7. And so to get the pH of that, you take the minus log of it. Take the minus log of that number, you get 6.81. And that's to three, sorry, not 3 significant figures, to 2 decimal places as the question asks us. Okay, I think it gives you 6.809, something or other. So obviously you've got to round that up to 6.81. Right. Okay, so predict with a reason whether water is acidic or alkaline or neutral at 310 Kelvin. Right, so they're trying to trick you into thinking, that that is less than pH 7. So it's acidic. Well, it's not acidic at that point because it is neutral. Why is it neutral? It's because H plus ion concentration is equal to OH minus concentration. That is what the definition of a neutral solution is, and that's what will be there. Okay, predict with a reason the sign of the enthalpy change for the ionization of water. So I've written the equation down there that they've used. So for H2O, going to H plus and OH minus. And we've got Kw is equal to the concentration of H plus multiplied by OH minus. Right, let's see what happens as you increase the temperature. Right, at 298 Kelvin is 1 times 10 to the minus 14. You increase it, it goes up to 2.4 times 10 to the minus 14. It gets bigger. So what that means, when you increase the temperature, this equilibrium, right, Kw gets bigger. So that means the concentration of H plus and OH minus, they're both bigger. So that means when you increase the temperature, the equilibrium moves to the right when you increase the temperature. And now Le Chatelier tells us it must be opposing the change. So when we increase the temperature, the equilibrium moves to the right, so it must be endothermic in the forward direction. So that means the enthalpy change for the ionization is endothermic, so it is positive, isn't it? That's a fairly standard question there. Okay, that's what they want you to say there. Right, no, just that's the right answer. And that's the end of it. I just want to point out that sometimes people tend to give a wrong answer there. They say it's endothermic because they say that you are breaking a bond, which is a little bit not quite right, is it? Because really, though what I've just written down there, H2O going to OH minus and H plus, is a simplification of that. Because what's really happening is you've got two H2O. I'll do a blue one and a black one. Let's say that the black one is going to give away a proton to the blue one. So that's going to form H3O plus. That's what's really happening there. I'll draw that properly. Okay. So what we've got. So it is a bit, you can't just say that you've broken a bond, because that's not, strictly speaking, what happens. Yes, you have broken a bond. You've broken, say, that bond, but you've also formed a new bond, that one there. So that's not the right answer, is it? You've got to use Le Chatelier's and equilibrium to explain it that way. Okay, so that's about halfway through the paper there. So I'll stop there and continue in the next video.